Today we're going to talk about inverses of functions. So first, before we get into inverse functions, we're going to talk first about what an inverse is. So a more general term for inverses is an inverse relation, and that's the result of exchanging the input and output values of a relation. Now I say the word relation and not function because not necessarily all inverses are going to be functions. But when you do have an inverse relation that is a function, that's when you have an inverse function. Let's take a look at our classic example, y equals x squared, and we are going to graph that and its inverse as well. So since we know that an inverse is going to be the result of exchanging the input and output values, we are going to first come up with a table of values for y equals x squared, and then we will go ahead and swap the input and output values to get a table of values for the inverse. Let's start with y equals x squared. So let's plug in some values. So plug in 0, 0 squared is 0, plug in 1, we get 1, 2, we get 4, 3, we get 9. Let's put some negative numbers in there. So negative 1 squared is positive 1. Negative 2 square that, you get positive 4. Negative 3 square that, you get positive 9. Okay, so now graphing all these points that we just found to come up with our graph. So 0, 0, 1, 1, graph all those points on there, and we can see that we have this parabola. Now for the inverse, we are going to swap the input and output values, so the x and y get swapped. Now 0, 0, and 1, 1 is going to be the same, but then for 2, 4 becomes 4, 2, 3, 9 becomes 9, 3, this becomes 1, negative 1, 4, negative 2, and 9, negative 3. So now let's put those points on. I'm going to do it in a different color so we can differentiate here. 0, 0, 1, 1. Put all those points on your graph, and you can see we have what looks like a sideways parabola. Now, a couple things to note about this. First, there is clearly some sort of a relationship between these two graphs. Right, it is some sort of reflection. It's actually a reflection in this line here. Another thing to notice is that the inverse of y equals x squared is not a function. And we can see that easily by looking at that red function that I just graphed and applying the vertical line test to it. It doesn't pass the vertical line test, which means this is not a function. So that's an example of an inverse relation that is not a function. Okay, so you can graphically just say that this is the result of reflecting the graph over the line y equals x. Okay, a couple things to make note of inverses. So first, a quick shortcut way to determine if a graph's inverse is going to be a function, you can use the horizontal line test. So with that last example, instead of having to graph the inverse and then apply the vertical line test, you could have just used the horizontal line test on y equals x squared, on the yellow function there. The horizontal line test works the same way as the vertical line test. It's simply, if it doesn't pass the horizontal line test, if there's some way that you can draw a horizontal line that goes through the function in more than one place, then you know that the graph's inverse is not going to be a function. In terms of coordinates, if a comma b is a point on the graph of f, then b comma a is a point on the inverse of f. In terms of notation, when we talk about the inverse of function f of x, we use this notation with a negative 1 that looks like an exponent. And just know that that notation refers to the inverse, and it does not mean that f of x is now in the denominator. And then in terms of how you can find the inverse of a function algebraically, we were able to just now find it in a graphical method. But we want to find the inverse of a function algebraically. That means we want to find the function rule. Then we want to start by writing everything in terms of x and y. So if anything's written in terms of f of x, change f of x to y. Then you are going to swap x and y. So anywhere you see an x, you replace it with a y. Anywhere you see a y, you replace it with an x. and then you'll solve for y. Now, if the result is a function, then you will write your answer with function notation. So you would write f-1 of x. If it's not a function, you can just leave it in terms of y equals. Take a look at example 1. Find the inverse of f of x equals 3x minus 2. So we are going to do this algebraically, so we'll start by writing everything in terms of x and y. So we're going to change that f of x to be just y. Now we swap x and y. So we see a y here, we're going to replace that with an x. We see an x, we replace it with a y. So this is x equals 3y minus 2. And now we solve for y. Get y by itself. So add 2, divide by 3. We have x plus 2 over 3 equals y. Last step, if the result is a function, then write your answer in function notation. So y equals x plus 2 over 3, is that a function? Now the quick way to determine whether or not it's a function or not is there any value of x for which I can plug in and get 2 different values for y? Not in this case, so we can write this with the f inverse of x equals x plus 2 over 3. Alright, so function inverses. If the inverse of a function is also a function, then these functions are what we call one-to-one because inputs and outputs are unique. Right, so normally in a regular function, if you have some values of x, each value of x gives you a unique value of y. There's only one y value that it maps to. Now, if the inverse of the function is also a function, that means each of those y values gives you unique x values. So for each y value, there's just one x value. So we call this one-to-one because if you were mapping one input to an output, each input maps to one output and each output maps to one input. So there is a one-to-one correlation there. Now, there is a quick way using composition, which we talked about last time, to show that two functions are inverses of each other. And so the way that we can do this is composing one function into the other and doing it the other way as well. So if f composed with g of x is equal to x and g of f of x is equal to x, then you know that f and g are inverses of each other. Now the reason this works is because what you're doing is you're plugging in some value x into your function g, and you get some y value. And if f is in fact the inverse, then it should take that y value and it should spit back out the x value. And if it is in fact a function, then you are only going to get one possibility for that output. Otherwise, you would have multiple outputs and you would no longer be able to say that the function is one-to-one. Alright, so to check if two functions are inverses, compose in both directions and check if the result is x in both cases. Let's do example 2. Show that f of x equals 3x minus 2 and g of x equals x plus 2 over 3 are inverse functions using composition. So we are going to compose the two functions in both directions and show that it is equal to x at the end. So if the inner function here is g of x, we are going to plug in x plus 2 over 3 into the function f. So this would be 3 times x plus 2 over 3 minus 2. Multiply that, and it looks like the 3's cancel. You're left with x plus 2 minus 2, and 2's cancel, and that leaves you with x. Let's do it the other way. So g composed with f of x. Now f of x is the inner function, so we are plugging in 3x minus 2 into our function g. This gives you 3x minus 2 plus 2 all over 3. The minus 2 and plus 2 cancel. That leaves you with 3x over 3, and that's equal to x. And so we've shown using composition, because we've done it in both directions, that in both cases you end up with x, and that tells us that these two are in fact inverse functions because you are plugging in some input x into your function g that gives you a value y, which then your function f takes, and if the function f takes y and spits back out x, then we know we have inverse functions. We had to do it in both directions in order to show that both of them are in fact inverse functions.